Okay, so in this video we're going to be looking at how to understand trig functions using circles. And the idea behind this video is to really show you how and why the sine function does what it does. Why does the cosine function, why does the tan function look like it does? Why is sine naught naught? Why is sine 91? Why is cos 90 naught? Why is tan 45 1? Why is tan 90 undefined? All of those questions that we are so exposed to when we deal with these functions that we don't actually know why they are true. And in this video I want to show you why they're true by using a circle. And you can see here I've got what is known as a unit circle. And a unit circle is a circle that has a radius of 1 unit. You can see here from the center of the circle to the point of the circumference, the distance is 1 unit, okay, which makes it a unit circle. And you can see here, if I draw a line or a radius from the center to a point on the circumference, you can see that that point on the circumference can be identified by particular coordinates. And those coordinates, there will be an x component, okay, and there will be a y component, okay. So for example, this point over here, 0,866 and 0,5 has an x component of 0,866 and a y component of 0,5. So you can actually construct a triangle, okay. You can see that. So if I change the radius, okay, you can see I've got a different triangle, okay. But the idea is your radius becomes the hypotenuse of your right angle triangle, and the x component is just the x coordinate and the y component is the y coordinate, okay. So just by changing the radius, you can create a different triangle with different dimensions, but all the triangles that you create will always be right angle triangles, and your hypotenuse will stay the same. Why? Because the hypotenuse is just the radius, and the radius is the same, and the radius in this circle is just 1, so your hypotenuse will always be 1, okay. And one of the ways to describe the radius that we are drawing is to compare it in terms of an angle with respect to the positive x-axis. So this particular radius makes an angle of 55 degrees with the positive x-axis, but I can change the radius, okay? I can bring it closer to the x-axis, so now it has an angle of 30. Now it has an angle of 15, and now it has a bigger angle like 78, 80 degrees. But the idea is that by changing the angle between the radius and the positive x-axis, we change the dimensions of my triangle. And because we change the dimensions of the triangle, we change the coordinates of the point of the triangle, because those coordinates are a reflection of the x and y components that make up that particular point. And it's this triangle that we're going to make use of to determine what and why the trig functions look like they do. So let's get started, okay? So if I take the sine function, we know sine is defined as opposite over hypotenuse, okay? So in this particular triangle, the opposite side, if this is theta, is going to be this side, which is the vertical side, or in other words, just the y coordinate, okay? Because this y coordinate is just this y distance from the x-axis to that point, okay? So the opposite side is just the y coordinate, just like the adjacent side is just the x coordinate, okay? And the hypotenuse is obviously 1. So sine is just going to be the opposite over the hypotenuse, but the hypotenuse is always 1. So when we're trying to look at sine, we only really have to look at the hypotenuse in this particular situation, okay? Because the hypotenuse is fixed, it's always 1. So what happens when we make theta naught? Okay, so when we make the angle between the radius and the positive x-axis naught, what you can see is that the opposite, which is the represented by the y coordinate, is naught. Okay, which means that if we say sine of naught degrees, that's going to be naught over 1, which is naught, which is why the sine graph at an x value, at a theta value of naught, is naught. That's why the sine graph starts at naught. Okay, and what we can see that the sine graph actually increases as we go on towards the right on the graph. As we increase the value of x, the sine graph actually increases, and that makes sense because as we open up the angle here, as we change the triangle, as we open up the angle of theta, can you see how the opposite side is increasing? Can you see that the opposite length, the distance, is increasing as we open up this angle, as we increase this angle closer and closer to 90 degrees? And this is reflected on the sine graph. As we increase this angle, till 90 degrees, the sine graph increases. And now, if we make the angle 90 degrees, okay, if we actually make theta 90 degrees, what do we notice? Well, we can see here that the opposite, which is represented by the y-coordinate, is now 1. It equals the distance of the hypotenuse. And that is why sine of 90 is 1. Because sine of 90 is just going to be the opposite over the hypotenuse. But when the theta is 90, the opposite equals the hypotenuse. So therefore, opposite over hypotenuse is just 1, which is why sine of 90 is 1. Okay, so you see, you can start seeing why these particular uh, results exist. So why is sine 91? It's because of this relationship that I'm showing you on the circle. So let's continue. Let's make the theta bigger. Let's increase it. So what we notice is that now the opposite side is decreasing. Okay, decreases, 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 and we see this on the sine graph. The sine graph starts to decrease because the opposite side is decreasing. And then when we get to an angle of 180 degrees, we notice that the opposite side is now naught, which is why the sine graph is naught. Okay, and then when we increase the angle further, we start seeing that the opposite side now becomes negative. You can see the y-coordinate is now negative, and we see this on the sine graph. The sine graph is now negative, and we can also see that the y value starts to become further and further away from naught. We can see that it gets further and further away from naught, and this happens on the sine graph until eventually at 270 degrees, the opposite now becomes 1. At 270 degrees, the value of the opposite side is now 1, or negative 1 to be more specific, which is why at 270 degrees, the sine graph is minus 1. Okay, and then what happens is that as we go further, as we increase the angle towards the end, 360, the opposite then decreases. It goes closer and closer to 0. So a negative number that gets smaller or closer to 0 is essentially increasing, and we see this on the sine graph until eventually we get to 360 degrees, or to where we started, where the sine graph is naught. And we see now the sine graph starts to repeat itself. Isn't that amazing? Now, something else that I want to draw your attention to is, do you see how with the sine graph, the opposite side never exceeds the hypotenuse? It only equals the hypotenuse at 90 and at 270. Do you notice how it never actually exceeds the hypotenuse? And that's why sine as a function can never ever be greater than 1. Okay, because for sine to be greater than 1, that means that the numerator must be bigger than the denominator, but we know that the opposite side can never be bigger than the hypotenuse, which is why sine can never be bigger than 1. Okay, and it's the same thing for cos, and let's look at cos now. So with the cos function, cos is defined as adjacent over hypotenuse, right? So in this case, we said that adjacent is just the x-coordinate, and we can see that here. The x-coordinate is the adjacent side. The x-coordinate is corresponding to the adjacent side. And what we can see is that when we make theta naught, so the angle between the radius and the x-axis, the positive x-axis, when that is naught, we see that the adjacent side is now 1 because the x-coordinate is 1. And that explains why the cos function is 1, because the cos naught is just going to be 1 divided by the hypotenuse of 1, which is 1, which is why the cos graph starts at 1. Okay, and then as we increase the value of theta, the adjacent side starts to decrease. Can you see that? Adjacent side starts to decrease until eventually we get to 90 degrees where the adjacent side is naught, and that explains to me why the cos graph is naught at 90 degrees. And we said how the adjacent side gets smaller as we go from a theta value of naught, and we see this reflected on the cos graph. The cos value gets lower and lower and lower until we get to 90 degrees when the cos graph is naught. And then after that, we start seeing, as we increase the value of theta, that the adjacent side is now negative. Can you see that? The adjacent side is now getting further and further and further away from naught, but it's negative. It's negative. And we see that here. It's getting further and further away from naught, the cos graph, until it gets to minus 1. And that happens at an x value of 180 degrees. Okay, because at 180 degrees, the adjacent side has a value of minus 1. So if we say cos of 180, it's going to be minus 1, which is the adjacent side, divided by the hypotenuse, which is 1. Minus 1 over 1 is minus 1, which is why cos 180 is minus 1. You see where these things come into play now. And now if we increase the angle of theta further and we go beyond 180, we see that the adjacent side is now becoming smaller, or in other words, closer and closer to naught, okay, until we reach 270. And we can see this on the cos graph. It now becomes closer and closer and closer to naught until we reach 270 degrees, where at 270 degrees we see that the adjacent side is a value of naught. And if the adjacent side is naught, the numerator is naught in the cos function, which is why cos 270 is naught. Okay, and now if we increase it further back to where we started, we start seeing the adjacent side now increases. Can you see that it's positive and it's increasing, 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 increasing until we get back to where we started, and now it gets back to 1, and then the cos graph starts all over again. How wonderful is that? I just think that's absolutely amazing. And again, can you see the adjacent side never exceeds the hypotenuse? It never exceeds the hypotenuse in magnitude, which explains why the graph never exceeds 1 or minus 1. It never exceeds that. Because for it to exceed 1, the numerator must be bigger than the denominator. And the adjacent side is never bigger than the hypotenuse, which is why the cos function never exceeds 1. Okay. Now let's look at the final function, which is the tan function. Okay, so the tan function looks very different to the others, but we're going to go through it. And we notice that the tan function is defined by the trig ratio opposite over adjacent. Okay, and what we can see here is that the tan function starts off when x is naught, y is naught. Now, why is that? Now, since tan is defined by opposite over adjacent, we're not looking at the hypotenuse anymore. Okay, so we have to look at the x coordinate and the y coordinate. And since at a theta value of naught, we can see that the opposite side has a value of naught, because the y value is naught, which means that tan must be naught, because the numerator is naught when theta is naught. Okay, and then as we increase the value, as we increase the value of theta, what we can see is that the opposite side increases. Can you see that? The opposite side increases, but the adjacent side decreases. So opposite increases, adjacent decreases. And if you try this on your calculator, if you increase the numerator, okay, and you decrease the denominator, the number becomes bigger and bigger and bigger and bigger. And we see this on the tan graph. It becomes bigger and bigger and bigger and bigger. But what I want to draw your attention to is when we make theta an angle of 45 degrees, okay? Because when theta is 45 degrees, it's something very special happens in the tan function. If this is 45 degrees, right, it's the angle between the radius and the positive x-axis. This is 90. Therefore, this also has to be 45 degrees, right? And if this is 45 degrees, that means that this is the base, these are the base angles of an isosceles triangle, which means that these two sides must be equal. These two sides must be equal to each other. And if these two sides are equal, that means opposite is equal to adjacent. And if opposite is equal to adjacent, then the tan function is 1. Because opposite equals adjacent, and tan 45 is opposite over adjacent. And if opposite equals adjacent, then tan 45 is 1. That's why tan 45 is 1. We can see that here, tan 45 is 1, because the opposite equals the adjacent when we have a theta of 45 degrees. How wonderful is that? But now let's increase theta. Let's increase theta to 90. And what we notice as we go towards 90, do you notice how the opposite gets bigger, right? But the value of the adjacent side becomes smaller and smaller and smaller. And when you take a big number and divide it by a very, very small number, your number becomes much bigger. And you can see this on the tan graph, and you can try this on your calculator. And the closer and closer we get to a theta value of 90, the bigger our number becomes. Okay, the bigger our number becomes until we get to a theta value of 90. And here, our adjacent side is a value of naught. But now tan is defined by opposite over adjacent. But at 90 degrees, adjacent is naught. So therefore, at tan of 90, it's going to be opposite over naught, which is undefined. And that is why tan of 90 is undefined. It's because the adjacent side at an angle of 90 degrees is naught. And you can't divide by naught, therefore tan of 90 is undefined. How wonderful is that? That's just, I just think that's amazing. Okay, let's increase theta. As we increase theta, what you notice is that the opposite side now decreases, okay? The opposite side decreases, but the adjacent side increases. So the number actually becomes smaller. But since the adjacent side is negative, we have a negative number that is becoming smaller. And a negative number that becomes smaller, which goes closer to naught, a negative number that goes closer to naught is actually increasing. Think about it. A negative number that goes closer and closer to naught is actually an increasing function. And that's why as we go from a theta value past 90, we see the tan function is negative, but it's going closer and closer to naught until we get to a theta value of 180, where the opposite side is now naught, and because the opposite is naught, tan is naught because opposite is in the numerator. Okay, and then we see the tan function starting to repeat itself because tan is a period of 180 degrees. Okay, and that's just because if you really want to think about it, the negatives will cancel out. Okay, so you've actually got positive functions here because the opposite over the adjacent is still going to be positive because it's negative divided by negative, because it's the y over x, right? It's the opposite over the adjacent, and they're both negative, and negative divided by negative is positive, which is why the tan function is still positive even after 180 degrees. Okay, so that is the tan function, and you can see here as we go to 270 degrees, here over here the adjacent is naught, which is why tan of 270 is also undefined because we can't have dividing by naught, it's undefined. Then as we go back to 360 degrees, we see a negative function going closer and closer to naught, which is increasing, which is why the tan function is actually always increasing. Okay, so I hope you can appreciate now why these trig functions look like they do. It's not just about what they do. Now you actually understand why they do what they do, and I think that's such an amazing thing. In mathematics, you'll be exposed to lots of facts, lots of things that they'll tell you, but to actually understand where those things come from is such a powerful and such a rewarding thing, and I think it makes your experience of maths much more enjoyable. And I urge you, take that approach of understanding. You'll not only enjoy maths more, but you'll probably do better at it. Hope you enjoyed this video. Hey guys, this is Ilyas from Tutonic. Just a reminder to keep on spreading the word, telling your friends about the organization, and I hope that you enjoyed this video.